I know. Psychology for the share.
I've never walked so fast in my life.
Why?
Because I got the bus.
Betsy, if you listen to the live stream, that's not
No
live.
sound, just so you know.
That is not the live stream. That is last week's video. Right there. Should have sound now.
Yeah, I've got the bus. It's 5 to 5.
I know. I might.
Is there sound?
I was rushing.
You won't cover any session. What's it listen to that week after?
Being deaf.
I thought so. You did tell me I put
Like for an hour. But it's so empty anyway. I think
Look, I dropped this one.
You got this one? Oh no, you got
She drank both of those drinks. I was about to say. I feel like I'm Spider-Man on the roof. I got no problem here. We got you viewers.
find out.
I got no viewers. I think you. No, I got viewer again.
Right, do you know when the exam is?
2nd of June.
Yes. We're prepared and ready.
Somebody has actually said, Connor is here. Somebody has sent me an email yesterday asking me when the exam was. Well, I don't
Oh,
know
that's
the
because
exam.
there's 2
Do I have to
days.
find the time?
There's 2 dates. One's for the design engineering and then one's for the product design. So that's why we're confused.
Really?
Yeah, there's one on the 25th of May and there's one on the 2nd of
Is
June.
it design or indie or?
Indie. One of them, like someone's got it on a different date to the product design people, which is probably why people are confused.
Oh, thanks for telling me. I looked it up. Should be 1 day. I'll find out.
Okay.
Should be 1 day because there's only one exam. So there are 2 exam days, are there?
Yeah, I think.
Materials and processing.
Yeah. But I think it's different. Like, so product design have it on the 2nd of June, and I think like design engineering or someone else has it on the 25th. I'm not sure.
Should not be like that.
May.
It should be only one exam. Anyway, listen, we don't have any say in when the exam is. We are not even told. We are told at the same time as you are. So make sure you know where it is, because from what I understand, it's not here. It's somewhere in Holdenhurst Road. Make sure you know where it is. Make sure you get there on time.
Citygate.
Yeah.
Yeah, have you been there?
I've been there because I did student rep training there,
Oh,
but nobody else has been there.
no. I mean, I've never been there. Hey, listen. Make sure you go and find a place beforehand, because it's early in the morning.
Is it?
What
time's it?
All right, have you done your revision?
Yeah.
Totally.
Ready?
All of it.
Now?
Yeah. Let's do it.
Let's go Citygate now.
I'm going,
Free room.
Let's do it.
I'm going to do a revision of basically the areas that are in the exam, which are all the areas that we covered, essentially. But perhaps it will help you to revise the sort of thing you need to revise, or in each topic, all the topics are covered. But in each topic, the type of understanding and knowledge that you need to have probably be had now by this revision. First of all, let me tell you about the structure of the exam. You'll be getting a number of questions, possibly 7 questions, and you have to choose 4. Right? in one of the past exam papers, it says 5, but that was many years ago. You probably get, anyway, read the Ruby very carefully and do what it tells you. You probably get 7 questions and you have to answer 4. That means each question has 25 marks. The topic we covered started with basically the very fundamental structure of materials. Fundamental structure of materials goes to atoms. I'm not going to go through the structure of atoms because you all know it, but you need to have some appreciation of the structure of atoms in order to understand the way atoms are bonded or joined together. Just a reminder, the atoms are made up of protons, i.e. the nucleus, what is in the nucleus, which essentially is positive, and electrons that go around the nucleus and are negative. All bonding, i.e. atoms joining each other to make solids or liquids or gases, is to do with the way these electrons interact. Materials that we deal with are solids, really. We don't deal with liquids. Certainly not in design. So we start with the way atoms join together, i.e. atomic bonding. Sorry. There are 4 different atomic bondings. Come on, Eric. Atomic bonding. Which one do you want to start with? Okay, you start with. Covalent. What is a covalent bond? Yeah, covalent as in CO, i.e. sharing. They share electrons. Now, the essential thing you need to know about covalent bonds is that the electrons are engaged, i.e. they are not free. Right? If the electrons are not free, it means you don't get any conductivity, or very little conductivity, because electrons on the whole are engaged in sort of bonding to each other. To free an atom, you need a lot of energy. You have to excite them. On the whole, covalent bonds electrically are no good. There are no conductivity. No heat conductivity, no electrical conductivity of this. The other implication is that they are strong. They are held together using these bonds, these shared electrons. So this is what there are lots of things about covalent bonds, but in terms of material, what I just said is what you need to know, right? Examples of covalent materials. Come on. Give me some examples. What? Yes, something a bit more applied to you, something more relevant to you. Covalent bonds. Covalent bonds are covalent bonds are the basic structure of polymers, polymer chains. In a polymer chain, atoms are joined together using covalent bonds. Okay. For example, in ethylene is a molecule. In ethylene, that forms polyethylene when you join lots of them together. In ethylene, carbon and hydrogen atoms are bonded together using covalent bonds. Or the backbone of individual chains within the chains, not between the chains, within the chain, you have covalent bonds. Next one. Metallic bond. Okay, metallic bond is perhaps the most interesting one because in metallic bonds, the outer shell electrons, the very outer shell electrons are all shared between all the atoms. The electrons don't belong to any one particular atom. As a result, they are anybody's, so to speak. Not all the electrons, only the outer shell electrons. As a result, they can move. They can move about quite freely. And that means, if they move about, means metallic bonds can conduct both heat and electricity. It also means that they are, although they are strong, but they are not as strong as covalent and ionic bond that we'll mention in a minute. Because they are all basically positive and are all about the same. Okay. The essential thing you need to remember about the effect of metallic bond on the property is that if these are the centers, the atom centers, they're all positive. Okay, and the electrons, especially the outer shell electrons, the very outer shell electrons, they're all over the place. They all give the outer shell electrons which conduct electricity. But it also means that for these atoms, there are no preferred position, so to speak. For this atom, it doesn't make any difference whether it's here or there or there. They're all positive, they're all the same. That means metals are basically ductile. They can be deformed. The other, sorry. Then this one. The other bond, the other important bond is the ionic bond. In the ionic bond, atoms don't share electrons, they exchange electrons. One atom gives, the other atom receives. So as a result, one becomes positive, the other one becomes negative. The one that has accepted electrons becomes negative, the one that has given out electrons becomes positive. So you end up with an arrangement like this. Positive, negative, alternatively. Now, positive charges like to be negative, like to be near negative charges, and vice versa. As a result, these are very strong bonds. They like to be where they are. If you try to move them, move this from here to there, from here to there, then you're moving it away from where it wants to be to somewhere it doesn't want to be, because if you move this from here, it wants to be here because they're attracted to this. You'll be trying to move this towards a negative charge, a like charge, a one that doesn't like. So it is very difficult to deform. These ionic bonds are hard. Most ceramics have ionic bonds. Again, in this like of electrons, all the electrons are basically busy bonding. Bonding the atoms together. I.e., there are no free electrons. As a result, no electrical conductivity, or very little electrical conductivity and very little heat conductivity. The three bonds I mentioned, covalent, metallic, and ionic bonds, are known as the primary bonds. The primary bonds. Before we go to secondary bonds, can you very quickly remind yourself, why is it that plastics, polymers, I said polymers, within polymer chain you have covalent bonds. And I said covalent bonds are strong. But how come polymers are relatively, plastics are relatively easy to bend, easy to deform, relatively weak? Although I just said the bondings are strong.
Because the monomers together.
Absolutely. Thank you. Because the covalent bond just bond the monomers together, molecules together, not the chains together. So you have sort of bits of chain or lengths of chain, right? Of these atoms that are bonded together due to the covalent bond, but one chain is only very loosely bonded to the next chain. This loosely bond that I just mentioned is called a secondary bond. Secondary bonds are those bonds that are not from basically primary attraction. They are as a result of very small differences in electrical charges. For example, a very good example that generally books give is if you look at a molecule of water, right? If you remember, it has one oxygen and two hydrogen, right? Within this, you have obviously covalent bonded. Hydrogen, these two hydrogen are covalently bonded to this oxygen. These bonds are quite strong. But now consider two molecules, two water molecules. Each is electrically almost neutral, but these hydrogen atoms are not symmetrically bonded to hydrogen. In other words, they are a little bit lopsided, exactly the way I've shown it. You know what I mean? They are not, they are not symmetrical, they're lopsided. Hydrogen, this side, is a little bit more positive than this side. This side is a bit more positive than this side. This side of the molecule, right? Consequently, only slightly, not a lot. Consequently, this side will be attracted to this side of the next molecule, and this is how it goes on. And this side of this molecule will be attracted to the negative side of the next molecule. This way, these molecules of water are held together. But the bonding is weak. A little bit of, if you like, excitement, a little bit of agitation disturbs them, and in fact destroys them. Like, for example, they are very temperature sensitive. A little bit of change in temperature, rise in temperature, the bonding goes away and they float all over the place. Okay. This type of bonding is known as a secondary bond. The bonding between the various parts, the various chains in a polymer is of this type. That's why they are not very strong. And that's why they are fairly temperature sensitive. Okay. You know, these are the essential things to know about the atomic bond. But you must know the effect of these things on the properties of material. As I've already said, with polymers, you know what you get with polymers, you get generally two types of bond. You get the covalent bond within the chains, and the secondary bond between the chains. Metals all have metallic bonds. Ceramics have mostly ionic bond, but also sometimes covalent bond. Okay. Before I move away from this, last week I talked about semiconductors. Remember? What was a very common semiconductor? What is a very common semiconductor? I spoke about this last week. Silicon. Silicon joins the other silicon using covalent bond. It has 4 electrons. These materials, although they have covalent bond, and conductivity is very difficult, almost 0. If you excite them, occasionally you can encourage one electron to jump or move from what we call the basically valency bond, i.e. the bond that holds the atom together, to the conduction bond, i.e. free itself and conduct electricity. But it is very rare and very difficult, and the effect is very small. Silicon on its own may be persuaded to do a little bit of conduction, but it's very small. It's not as you want to measure. But if you dope it with select elements like phosphorus or aluminium, then you can increase that ability for the free electrons or conducting electrons to go out there and cause conduction. It's still nothing like a conduction that you get in a metal. Nothing like that. You're talking about 100 times less, hundreds of times less. But it's still measurable conduction. And you do that by what? Adding dopants. Things like, as I said, aluminium, phosphorus, arsenic, that type of thing. All right? So when you talk about atomic bonding, remember situations or exceptions like semiconductors. Okay? Any questions on atomic bonding and the effect on properties? Really must understand. Nothing very difficult, but just basically what I said. The next step, or the next stage of sort of solids getting together, were crystals. One of the implications of this metallic bonding is that they tend to form a very regular, a very ordered structure. As a result, metals that have a metallic structure are known as crystalline material, ordered materials. That means the atoms in metals have some sort of order. They have definite rows, definite columns. Right? The way they're ordered depends on the material. Aluminium has a face-centered cubic structure, iron has a body-centered cubic structure at room temperature, and so on. And again, you need to understand that and appreciate that. Okay, can you think of any examples for, so how many structures have we got in metals? Do you remember? How many structures in metals? Body-centered cubic structure, face-centered cubic structure, and hexagonal closed packed. All right.
Sorry, Kyle, can you repeat those methods?
Body-centered cubic, they're all on my EU. Body-centered cubic, or BCC, body-centered cubic. Or iron at room temperature. and face-centered cubic structure, FCC, face-centered cubic. Okay, I will draw the picture if you remember. Because basically, the arrangement is that the atoms are at the, if you like, corners of cubes. In body-centered cubic structure, you have an atom at the corner of the cube and plus one atom at the center of the cube. In face-centered cubic structure, you have this cube, obviously with an atom at each corner, plus an atom at the center of each face. Body-centered cubic has the atom at the center of the cube. Face-centered cubic has the atom at the center of the face of the atom. If you go to my view, very clear pictures of this. Hexagonal close-packed, as the name suggests, has a hexagonal structure. It's sort of they are layered of atoms in hexagonal arrangements. You know what an hexagon looks like? Yeah, you know what hexagon looks like. So you have an atom at the corner of each hexagon with an atom at the center of it. Imagine layers of it, one on top of each other. All right. Generally, the atoms, metals, common metals are one of these structures. Probably the most common example of face-centered cubic structure is aluminium. The other one is copper. Hexagonal close-packed is less common in metals. Zinc is one. Titanium is one at certain temperatures, not all. Okay. Before we talk about different types of metals, etc., remember what I said. I said metals on the whole have a crystalline structure. Right? Because they have an order. And that gives rise to what we call a granule structure. Crystalline structure simply means, as I said, an ordered structure. The atoms aren't all over the place. They have certain positions. Okay. And this order doesn't just happen. This order starts right from solidification. When you cool, bucket of liquid metal, if you cool it enough, solids form. But solids don't form just all over the place. Solids form in a certain order. If you think of these as atoms, each square as an atom, one atom joins another atom, then the next atom comes and joins it in a certain direction, in a certain position, and the one after that, and then the one after that. And you see, eventually they sort of join each other to fill the space, become solid, you still have liquid in between. And when they join them on mass, they form what we call grains. So, very short time after cooling, a little bit later after cooling, further later still, And eventually when it's all cooled and solid, atoms are totally ordered. But they are ordered in different regions. Each region is a grain or a crystal, right? So if we look at a metal on a microscope, this is what we see. We see these regions, these grains. Generally, to deform a metal, you have to slide these atoms, as I said, you have to slide the atoms over each other. Imagine sliding this line of atoms and this line of atoms. Okay, this line of atoms slide nicely, easily, until it gets to this spot. When it gets to this spot, then it can't go any further because the direction of sliding will have to change from this direction to this direction. It's like, imagine cars moving in straight lines. If they're moving in straight lines, it's nice and they can go nice and fast. When they get to a sharp corner, they have to turn. The more corners there are, the more times they have to change direction, the slower and more difficult it is for their movement. That means the more of these changing directions we have, the harder the metal and the stronger the metal will be, the less soft it will be. The only way to have lots of these lines is to have small grains, smaller grains. That means finer grain materials are stronger and harder. Yeah, does that make sense? Yes, that is why fine grain materials are stronger and harder than the big grain materials, big grain metals. So you need to have some appreciation of the effect of the size of the crystal, size of the grain on the properties. Smaller grains, remember, smaller grains mean stronger, harder, also more difficult to deform. Okay. Any questions on the crystal structure? I might actually have these pictures of FCC. Okay, just you were saying. This is a body-centered cubic structure. The atoms at the corners with an atom at the center. If you look at lots of them together, this is the picture you see. Okay? But the same pattern. The same pattern. This is a body-centered cubic. BCC, body-centered cubic. Can you see it? And this is face-centered cubic. Cube, atom at the center of, at the corner, at each corner of the cube, plus an atom at the center of each face. Again, it's more difficult to see when you lump them together, but the pattern is the same. And finally, what I was saying about the hexagonal closed pattern. As you can see, it's not layers of this. Each layer is a hexagon with an atom at the center of it. And it is really made up of layers and layers of this. Because if you look at even this one, if you extend it in this way, it's the same. Except that the atom, this compared to that, has the same arrangement, so it's just one interatomic displaced. Okay. Generally speaking, as I said, generally speaking, metals we use in practice have lots and lots and lots of grains, and grains of materials we use, the everyday materials, are tiny, very small. Typically speaking, they are a grain in an aluminium alloy that we use, in a steel alloy that we use. It's about 40–50 microns. You know what a micron is? You know what a micron is, yes? Come on, please tell me what a micron is.
-6. So the -6.
-6 of a meter minus 3 of a millimeter. In other words, if you put 1,000 microns together alongside each other, you get 1 millimeter. Yeah? So a grain, typical grain is, well, I said about that. If you have a very fine grain material, grains may be as small as perhaps 10 microns, but that would be very fine. If you have a very coarse grain material, could be perhaps 100, 120 microns. I mean, typical materials we use in everyday design. It is very occasionally, if you have very special applications, you can manage to grow a component, a complete piece of component from one grain. If you manage to do that, then you get a really suitable property, because there are no grain boundaries. There are no grain boundaries are, as I said, there are barriers to deformation, but they're also areas of impurity, areas of basically junk and rubbish in a metal. But to grow a component out of just 1 or 2 crystals or grain is a very expensive process, and on the whole, it's only done under exceptional situations where the cost actually justifies the application. Rolls-Royce, for example, does that for some of their turbine blades, because they need extreme properties. They need very high strength, very tough properties, very hard properties. But as I said, that is not in an everyday material. Everyday material have tiny grains. Any questions on grains? Okay. I'm just showing various pictures, models of grains, to make sure you understand what the grains are and what the grain boundary, the border between the 2 grains is called grain boundary. In practice, if you look at the grains in a real metal on a microscope, this is what you see. It's like a mosaic, if you like, pattern, like irregular tiles, if you like, in real metal. Again, shown here, very elongated in some places. Okay. Okay, that is what you need to know about. That is what you need to know about the crystal structure of metal, the effect of the size. Remember the effect of the size, why we have a crystalline structure in metals, and so on. Okay, now that. Any questions on this? Any questions on this? Right. As I said, in real life, we really don't use pure metals. We use alloys. In other words, mixtures of metals with other things. Right. Any mixture of a metal is called an alloy. Steels are alloys, aluminium that we use are all alloys, brass and alloy. Titanium that we actually use is not pure titanium, it's an alloy. As I said, so for materials that we use in practice, we use alloys. Let's look at practical alloys that we use in design. Let's start with the most common one, steel. You need to have an appreciation of the various types of steel. As I've always said, we don't need to know the exact composition, but you do need to have an appreciation of the various types of steel. On the whole, what is steel? Taking for granted that we all remember what steel is. What is steel? Thank you. It's an alloy of iron and carbon, essentially. But tiny bits of carbon. And remember this. In common use, there are two types of steel. What I call basically the cheap ones, the low cost. By cheap, I don't mean necessarily cheap and nasty or low properties or inferior. They just cost less. We call them carbon steel, or sometimes they just call sometimes plain carbon steel. Okay. These steels haven't got any exotic elements. They haven't got any expensive elements. They just have iron with tiny bits of carbon, and perhaps some other common elements like tiny bit of silicon, tiny bit of manganese, tiny bit of magnesium, this type of thing. On the whole, the main ingredients are iron and carbon. And this is what you need to know. First of all, as I said, they are, relatively speaking, low cost. By that I mean they are about 50p a kilo, 30 to 40, 50, 60p a kilo. Okay, but say 400 pounds a ton. Right. And on the whole, there are three types which you have to appreciate. Probably the most common type of these is what we call low carbon steel. Can you read this? Yeah? Low carbon. Low carbon steel, as I've said, is the most common type of material we use. Mainly because we use a lot of cars. And cars have bodies, and car panels are still nearly all made from these. And I say nearly, only about 95% of them from this. As the name suggests, has very small amounts of carbon. It has between something like only this much carbon, 0.01 to maximum of 0.1%, not 1%, 0.1% carbon. Okay. This material is also, I put in brackets, is also, a lot of people call it mild steel. Okay. So what are the features of this material? I said they're low cost. They are very good materials to shape because it has very small amounts of carbon. It's relatively soft. It's very easy to press. Okay. It is maybe cheap. It is quite strong. It's certainly very stiff. It has a young modulus of over 200 gigapascal. It is a lot stiffer than even titanium alloy. Titanium alloy have a Young's modulus of about 140. steel or any steel has a young modulus of 200. A lot of applications. As I said, over 90% of car panels, car bodies. The second group of carbon steel, these are still plain carbon steels. They are known as the second type called medium. I just put C for carbon. Medium carbon steels. Medium carbon steels have about 0.1 to about 0.8% carbon. Quite a lot more than one. This results in them being stronger, harder, and for the higher carbon steels, a lot more difficult to deform. You can't really press steels with that much carbon. Perhaps 0.2%, 0.3% perhaps. These materials are used generally for structural applications, not car bodies. For car chassis, yes, perhaps. Chassis of a car. Beam for buildings, yes. So on the whole, they have good strength, they have good toughness, a lot harder than mild steel. And as we can see, they are hardenable. They can make them even harder than they are. They're still cheap. Still about the same price as that. I bought I don't know, RHA. We're doing some change in our house, taking walls up, so we have to put beams to support the walls. A beam about this big, this long. You know, it was 60, 70 pounds. Really cheap. Finally, high carbon steels. Sorry, this should be B. This should be B. We are still talking about plain carbon steel. High carbon steels. High carbon steels, in theory, have 0.8% and more. In practice, they have about 0.8% to 1.1. You don't see any steels with more than about 1.1, perhaps 1.15. Okay. These are high carbon steels. High carbon steels, again the same price, no more expensive. They really aren't much stronger than the medium carbon steels. They certainly aren't any tougher, but they are harder. For that reason, you should only go for them if you particularly want a lot of hardness. And if, for example, you want to make a very sharp blade, a very sharp tool, something that doesn't scratch, make a chisel, then that's a material. Okay? But as I said, the carbon, the more carbon you have, the stronger the steel comes up to a point. Once you get to about 0.8%, if you go any higher, you don't really gain anymore in strength. You gain hardness, but not strength, and certainly not toughness. These are very basic things. I'm saying it in very simple terms. These are the things you need to remember. Okay. These are the cheap, the low-cost steels. Yeah. All the other steels are classed and stupidly called alloy steels. As I said, it's a stupid term because all steels are alloy. No carbon steel is alloy. But commonly, only the steels that have some more special ingredients in them are known as alloy steels. In other words, alloy steels are more expensive. Alloy steels have more exotic elements: chromium, nickel, vanadium, molybdenum. These type of materials, the ones that I mentioned, are really the main ones. Okay. The most famous one group of alloy steels are stainless steel, as you know. Okay. So these are things like stainless steels. There are things like tool steels, proper tools. Oh, sorry, steel. Various materials. And so these have things like chromium, Cr chromium, nickel, vanadium, molybdenum, tungsten, etc. Not all at once, depending on the type you have. Okay, but not a lot more expensive. How much more expensive depends on the type. Okay, I'm not going to go through all this except for perhaps stainless steel, because I have talked about it. What's a stainless steel gun, especially? What is the magic element in stainless steel to make it stainless? Chromium. Chromium is a must for a steel to become stainless. Okay, generally, a stainless steel has at least 10–11% free chromium. And for various reasons, for it to end up with 10% free chromium, it must have at least 12% gross chromium in it. Okay. The cheapest type of stainless steel, that is called the ferritic one, or the, if you like, cold working stainless steel, has only got chromium in it. Nothing more exotic. Obviously, because it has some carbon in it, tiny amounts of carbon. But the main ingredient is chromium, other than iron. Remember, when you see steel, it is iron. But chromium, sorry, that stainless steel is good, better than mild steel, better than plain carbon steel in corrosion, but it's not the best. If you want a better stainless steel, much better one, then you have to add, as well as chromium, you have to add nickel as well. Again, you don't need to know these things in detail, but it is worth knowing that there are, on the whole, 3 types of stainless steels, 3 types. Main ones are perhaps other groups, but the main ones are the one I just what they call ferritic. I put SS for stainless steel. Ferritic stainless steel. It has just chromium, as I said, between 12 to 14% chromium. Then if you want a much better material, if you want better corrosion resistance, you have to pay a bit more and pay not just for chromium, but also for nickel, as I said. And that's because you add nickel, the material, the structure changes from ferrite to austenite. You get austenitic stainless steel. Austenitic stainless steels have between 17 to 20%, depending on the type, chromium, and between 7 to 11% nickel. Probably the most common one, sorry, by common I don't mean to be common and sort of cheap, quite very expensive. But the most usual one, the one that are used, if you go to supplier and say you want a really good stainless steel, what they give you is a 316 grade, which has 18% chromium and 8% nickel. A lot more expensive than mild steel. You're talking about, instead of paying, did I say stainless steel? Sorry. 10 carbon steel was 40p a kilo. That you're talking about 200 a kilo minimum or more. Right? A lot of very, very different things. But a lot better corrosion resistance. Okay. There is a way of telling whether it's a good grade of stainless steel or not by seeing if it is magnetic or not. This ferritic stainless steel, because it is ferrite, is ferritic, is magnetic, right? So it behaves like a mild steel. If you take a magnet towards it, it will attract the magnet, right? This one, because of this nickel in it, is austenitic. It means it's not magnetic. If you take a magnet to it, it won't attract it. Right? So that's one way of telling whether you're buying a good quality stainless steel. But be careful. The aluminium is also non-magnetic. The only material that is magnetic is ferritic steel. Ferritic, okay? Plain common steel. Aluminium obviously is non-magnetic. Copper is non-magnetic. Okay, I said there are three main types of stainless steel. Okay, are you okay with these? So that one cheap, what? Relatively speaking, this is still a lot more expensive than mild steel. As a mild steel of 40p a kilo, this will be probably about £1.50. This will be about £2.50 or £2 at least. So this is not cheap. It's still a lot more expensive than mild steel, but not as expensive. Okay, this is also known as the cutlery grade. Generally, canteen cutlery, cheap cutlery, are made from this. Not the posh ones. Posh ones are made from this. Okay. The third common stainless steel, or the one that people get in the market, is called the martensitic type. Martensitic stainless. Okay, the third one. The third one is called martensitic stainless steel. Can anybody remember what does that mean in terms of properties? I heard somebody say the right word. Come on. Somebody said hard. Yeah, martensite is hard. Remember that heat treatment we did in the lab? We heated it and dropped it in a bucket of water, quenched it. It became hard. Why did it become hard? Because the structure changed to martensite. Martensitic steel are hard, very, very hard. Remember, the hardness changed from about 200 in some cases to about 600. Martensitic stainless steels are very hard. They have a martensitic structure, martensitic grains. Okay, they are good for certain applications. They are hard. They are scratch resistant, very difficult to scratch them. They are not very tough though. And they are certainly not stronger than austenitic stainless steel. They are not tougher than austenitic stainless steel. They're just hard. They're just hard. So if you need an application, if you have an application which the material needs to be hard, then that's the material for it. It is hard and obviously corrosion resistant. This one, martensitic stainless steel, is like ferritic stainless steel. It only has chromium in it. About, I said, 14 to 16% chromium. But it's got a little bit of carbon and it's been quenched. So hardening. Okay. I said there are three main types of stainless steel: ferritic, austenitic, martensitic, right? There is actually a fourth one, but it's quite expensive. It's not very common. It's another one that if you want to write it, let me write it. Then it's called duplex. You know duplex? It's called duplex stainless steel. It's got a very complex structure. It's got some it's got chromium, it's got nickel, and it's got some other exotic elements. It's got possibly things like vanadium. The heat treatment causes it to be very, very, very strong as well as hard. So it's got the advantages of austenitic stainless steel plus some of the hardness of the martensitic. The problem with it is it's not very common and it's quite expensive. It's called duplex stainless steel. Okay, any questions on stainless steel? You're okay, you know the different part. Okay. Okay. If you have to make what shall I? I want to make some, say, bracelets. Can't afford silver. Of the type of materials I've talked about, what material would you use? Huh? What material would you use? Want to make bracelets? Brass. I haven't talked about brass, so brass would be one, yes. But of the materials I talked about, which one would you use? Of the ones I talked about, I haven't talked about brass. One of the stainless steel. Which one of the stainless steel? Remember, martensite is hard, but it is almost impossible to press. You can't bend it. I said it's martensite. So martensitic stainless steel, we can only cast it. Austenitic stainless steel, you don't want it to be magnetic either. You don't want a magnetic bracelet, do you? So I would say the answer would be, but you can argue as long as you're aware of what you're looking for. Okay. Remember, that ferritic stainless steel, and said another name for it, and a common name that people know it by is the cutlery grade. The reason for that is because they actually make cutleries from it by pressing it into shapes of spoon, fork, etc. Okay, let's go to the next common alloys. All right, much on that. Okay, next one is aluminium alloys. Okay, look, aluminium alloys, as the name suggests, are alloys of aluminium. So aluminium is the main ingredient with other things. On the whole, aluminium alloys are well over 90% aluminium. Right? Aluminium alloys, and you need to know their classification. It's very simple. They are classified in two ways. First of all, they are classified by the way they are produced. They are classed into what they call cast alloys and wrought alloys. There are two types of aluminium. Cast alloys and wrought alloys. And the names tell you everything. Cast alloys are generally made by casting. Now, and wrought alloys are by shaping, by forming. So these could be what? Could be rolled. What else? Come on. Somebody has said extrusion. Yeah, excellent. Extrusion is a very, very convenient method for. Anything else? Yeah, forging. Yeah. That's what you meant. Yeah. Forge. They're the main types. Obviously, you can roll them into tubes. You can roll them into strips, roll them into wire, etc. They're all rolled. Okay. These are examples. Okay. On the whole, which ones are stronger? Which group is stronger? Which group, cast ones or these ones, which ones are stronger? Wrought alloys, wrought ones are a lot stronger than cast ones. Remember that, remember that. Remember that. A lot stronger than those. Do you know why? Perhaps I then revise this thing. Cast structure, what I implied it. Cast structure, remember I said the atoms join each other, form grains, but in between, in the process, between the grains, I said all the impurities gather. Those areas of grain boundaries are full of rubbish, full of impurities, also full of porosity, full of tiny holes. As a whole, as a result, cast of all metals, not just aluminum, cast structures are not tough. Remember, cast structures are not tough. Cast structures are brittle. Right? They're not tough. They can be hard, but they're not tough. You certainly would not use a cast aluminium for something that needs sort of being hit, needs to absorb energy. And you should know about toughness. Okay. So if you want strength, toughness, to go to this one. I said there are two ways of classifying aluminium alloy. One was according to how they are formed. The other one is according to whether you can heat treat them or not. They are on the two headings: heat treatable and non-heat treatable. Okay. Heat treatable and non-heat. So you can have a cast alloy that's heat treatable. You can have a cast alloy that is non-heat treatable. You can have a wrought alloy that is heat treatable, wrought alloy that is non-heat treatable. Although in practice, cast alloys in practice, cast alloys are non-heat treatable. Okay, of these two, this is, I hope you appreciate, is the stronger one. That's why you heat treat it, to strengthen it. Okay. I don't expect you to know the grades and specifications. If you need them, you just go to suppliers and you say, I want heat treatable aluminium alloy, and they say, oh, you can have this one, or that. But heat treatable ones are stronger, much stronger. Generally, heat treatable ones have these. For example, one of the first heat treatable aluminium alloys was the 2020 or 2024 alloy, which is aluminium with about between 2 to about 4% copper. So I put examples. Not huge amount. Cu is for copper. Zinc and magnesium, about, I don't know, 2 or 3% zinc, 1 or 2% magnesium, not a lot more. So these are about, say, 75%, about 95% aluminium. The impurities are only about 5%. But that tiny bit of only 2 or 3% copper is sufficient to increase the strength of this aluminium alloy about 4 times. Okay, the heat treatment in aluminium, as I said, significantly increases the strength. It's 4 times sometimes, as much as 4 times. Okay. Non-heat treatable ones are a lot cheaper, obviously not as strong. In some ways, non-heat treatable, I haven't talked about welding to you. In some ways, non-heat treatable aluminium alloys are a little bit more convenient, because heat treatable aluminium alloy can't really, well, it can be welded, but if you weld those heat treatable aluminium alloy, then you have to do renew the heat treatment. You have to do the heat treatment all over again because you spoil the heat treatment. Therefore, many people say you can't weld aluminium alloys because of that purpose, but you can. You certainly can weld this group. But that group, if you weld it, you have to do secondary treatment, which is expensive, awkward, sometimes totally impractical because of the size. Okay. Aluminium. So this is what you need to know about types of aluminium. But can you give me some? Tell me something about properties of aluminium. Karen. Compared to steel, compared to other materials. What is special about aluminium? Lightweight, thank you. What light? The most important, among metals, the most important property of aluminium. Look, aluminium has a density of only about 2.7. Steel has 7.8. It's a lot of difference. Aluminium is a lot lighter. What else about aluminium? Come on, what else about aluminium? Special. On the whole or softer, aluminium is softer than steel, much softer than steel. Thank you. Yes, that's the other one. Weight and corrosion resistance. Aluminium does corrode, but a lot less than steel. I say lot, because it's a lot less prone to corrosion. Much higher corrosion resistance. Much higher. So light and corrosion resistance. Those are the two important properties of aluminium. Another important property has got a very high conductivity, both heat conductivity and electrical conductivity. Right? Not as good as copper, but very high. But the two main ones are the fact that it's light and the other one the fact that it doesn't corrode. But you do need to appreciate the way that it is formed. On the whole, if you want the strong ones, they are heat critical. Yes, I don't need you to know exact value, but you must have some appreciation of comparative properties of metals and other materials. I said, steel, or any type of steel, has a Young's modulus. Young's modulus tells you how stiff a material is, or rigidity. Has a Young's modulus of just over 200 gigapascal. Aluminium has a Young's modulus of only 70. You need to remember that. For structural use, if you want to have the same stiffness, if you don't want something to bend, then you have to use a lot more aluminium than you have to use steel to get the same stiffness and rigidity. Okay, but strength is not the same thing. Aluminium is not very rigid, but can be very strong. This aluminium, zinc, magnesium, this is an alloy which is 7000 series. It can have a strength of up to 700 megapascal strength. UTS, ultimate tensile strength, 700 megapascal. This is strength. My steel is only about 400, 500. Okay? Not the non-heat treatable one, not the non-heat treatable. But the heat treatable is a very strong material. Not very stiff, but quite strong. Okay? Remember that. So what do we about aluminium? Lightness, corrosion resistance, Young's modulus is very low. Strength depends on the heat treatment. can be very weak. It can be as little as 100 megapascal. For some non-heat treatable ones, perhaps 120, can be as strong as 750 megapascal. Okay, any questions on aluminium? I'm going to do part of the half of the revision this week and the next half next week. Okay, on aluminium. Okay, the next slot I'm going to talk about, the next slot, copper alloys. Some general properties of copper. Can you tell me general properties of copper? Very conductive, thank you, very conductive. What else? Corrosion resistance, very good, is good corrosion resistance. What else? Can be one of the most ductile materials, can be extremely ductile. Something else, not so much so positive. It's not cheap. So very high density. Very high density, thank you. Copper is heavier than steel. Okay? It's certainly not as strong as steel. It is not as stiff as steel, but it's heavier. Density of, what is density of copper? It's over 9. Well, you're looking at it. Depends on the copper. We don't use, okay, types of copper alloys. On the whole, copper alloys or copper that we use as a conductor in wires. Oh no, I should say as a conductor. In this case, when you use that, is what we call high purity copper. High purity copper is still not pure, but you can get the purity up to perhaps 99.5%, only 0.5% impurity. Okay. But that is not really what we use for products. In terms of products, what are the common copper alloys? Somebody said brass. Absolutely right. Probably the most common type of alloy. What do you need to know about brass? Brass, you need to know these things. A, brass is made from copper and zinc. Okay? Okay. Take it back. Can you read here? Can you read here? The two types of brasses, and you need to know that. What is called cold working brass? And hot working brass. Okay? The difference between them is as the title suggests. Cold working brass is much softer. You can press it, you can bend it, you can pull it, draw it. Hot working brass is much too hard for these any cold working. You can hot work it, You have to heat it in order to be able to work it. Or you can cast it. The reason for the difference is the amount of zinc that they have. Cold working brass has about 70% copper plus 30% zinc. Hot working brass generally about, well, start from say 65% copper plus 35%. Okay, so that 5% makes all the difference. Okay, what would you use this for? What would you use this for? They're both heavy. They're both heavy. So if you're saving weights, pop alloys on for you. But they're good, they look good. They're sort of golden color brass, corrosion resistant. Also the sort of density, weight gives them a little bit of activity. So it's one of the features for them. If you brass statue, the weight gives it a good feel. If you want to make it into shapes by punching, by stretching, by gluing, by pressing, use that. If you are happy to cast it or hot forge it, you can go to that. This one has got a much higher strength. Not as much ductility, but higher strength and harder. So this is relatively soft. So it scratches. This doesn't. Okay. Typical applications, the common applications are in plumbing. Not a very attractive example, but very practical. But if you look on my BU, I've got a section designed with copper, and you see lots of fancy products that have been designed with copper. Statue. The other type of copper alloys is bronze. Bronze is, generally speaking, bronze is copper plus, thank you, anything from 2% upwards. Same. And sort of the old-fashioned classical bronze has only about 2%. But now the modern bronzes have all sorts of ingredients in them. For example, there's an aluminium, something called aluminium bronze, which is a very good alloy. It is basically copper with 11%, well, not 11, that's just between 8 to 11% aluminium. Okay, so it's nearly is sort of 92 to 89% copper, the rest aluminium. It's a very strong alloy. It has got a very high corrosion resistance. It's got a very high strength, and it's quite attractive. Aluminium bronze. Copper is copper plus between 8, shall I say, and between 8 to 11% aluminium. Okay, the rest is copper. These These are the major copper alloys. They are not, or there are other types, but they are not as sort of commonly used. There is, for example, gilded metal, which is mainly for sort of aesthetic application, and mostly copper. It's copper with only about 5% zinc. It's a very soft material. It's a very reddish material. It's for aesthetics. Some parts of costume jewelry, items for home. Sorry, something I forgot to say. Bronze. A common application of bronze is making statues, obviously. Yeah, you've seen. And because it's heavy, it's got good feel. And said, I don't know what you brought. The density of copper, pure copper has a density of about 8.9, pure copper. For me, when you add things to it, you obviously change it, especially when you add as much as 30%. But in pure form, I think you find it's about 8.9. Quite heavy, and not heavy density. Perhaps a sort of off-market material, off-market copper alloy, not very common at all. It's called cupronickel. Cupronickel is about 70% copper plus 30% nickel. Making the material quite expensive. Very expensive. It's beyond the reach of sort of common products, but it's a very attractive material. It's got a yellow tinge. To me, nicer than even gold. Much nicer than pure copper. I said I don't know. To me, it's a chic shade of gold, if you like. It's nice. It's got that sort of remember dirty pink, dirty thing, that sort of shade. But it's very expensive. There are some cutlery made from it, very expensive cutlery. But having said that, there are certain applications, like some medical applications, where it is necessary, so where cost is not really an issue. The reason why it's expensive, because copper is expensive and nickel is very expensive. Of the materials I've talked about so far, nickel is the most expensive one. Okay, of the materials I've talked about. How do we shape copper alloys? Well, I've just said, if it's cold working, you shape it by pressing, drawing, rolling, etc. If it is hot working, by hot working, heating it, forging it, etc. Or casting it even. Any questions on copper alloys? If you've taken everything I've said in, you should be able to answer questions on these areas. I'm not finished. I'm just checking with. Okay, let's go a little bit of market. Titanium alloys. What is special about titanium? What is special about titanium? It should come to you. Sorry? Light. Very, not as light as aluminium, but a lot lighter than steel. Density of copper, oh, sorry, there is around 4.8. Still is 7.8. Not quite as light as half that of steel, but quite a bit light. What else? What else? What do you think of titanium when somebody says titanium? Corrosion resistance. So, okay, so light, very, very corrosion resistant, much better than stainless steel. So, corrosion. I'll talk about it. I'll talk about that in a minute. Yeah, it is, depending on the type. What else? What else? What else? What else? Come on.
Is it quite hard?
It can be very hard. Also, it's titanium alloys. Titanium alloy can be very, very strong. And very hard, can be very hard, provided it's being heat treated. There are, in practice, the titanium alloy that is used in products mostly is an alloy that often is known as the 4-6 alloy. It's titanium, so if you like, it's about 90% titanium, 6% aluminium, and 4% vanadium. Okay. Not pure. That can be heat treated to be very hard. It can be the weakest form of this has a strength of over 800 megapascal. The steel we tested had a strength of about 500, 600 maximum. Stainless steel we're about 600. If you heat treat it appropriately, but you lose, if you do that, you lose some toughness, you lose some softness. But if you can be heat treated to a strength of over 1,000 megapascal. Titanium is famous for its strength, surely, you know that. Somebody wants to make, they want to make something very strong, you make it out of titanium. You know the word titanium, where it comes from. The Americans call it titanium, and lots of people here now have started to call it titanium. You know why? You know why?
Greek Titans.
Somebody just said Titan. Titan is god of strength.
Yeah.
The Greek god of strength as well. Hence titanium, because it's titanium alloy. But the two problems with titanium. One is cost. Okay, with steel I was talking about 40p a kilo. With titanium, I think even the base price, you're talking about £8 a kilo and more. Treated processed titanium is even more. The other problem with titanium is that its surface is very, very difficult to machine. It forms a very hard surface because the reason why it's so good against corrosion is because it forms a very good oxide with oxygen. The minute you expose titanium to air, it forms this very hard oxide. Protects it against corrosion, but it protects it from machining as well. It's very hard to machine. You need diamond tape tools. Very expensive. It's actually expensive to process titanium. One reason why titanium is, the main reason why titanium is expensive is because of the processing. Titanium is not that rare on Earth. There are loads and loads of titanium on Earth. Okay? It's just expensive to process. Okay, so you have some appreciation of the cost of titanium, as I said, £8 a kilo, minimum, that is without any process. How much is aluminium roughly? I didn't mention aluminium, did I? About £1.50, that sort of price. Depending on the type of aluminium, very much depending. Certainly over £1 a kilo. £1 to £200. Look, as designers, you should be able to at least know how to find the cost of materials. I've said this before. There is a site called LME, London Metal Exchange. And Google it, LME. It's got the sort of hourly price of all the metals. All types of aluminum, stainless steel, iron, copper, whatever you like, zinc, LME, London Metal Exchange. Okay. Any questions on these? Okay, I'm going to finish for today. But before I finish, I just remembered one of the questions that I asked a few years ago. The question was this. Explain the significance of these properties of metal, not just metals, of materials in the context of design, What do these mean in terms of application? What does it mean? What is it and what does it mean? Some of them are obvious. Obviously, these are obvious. I mean, these should be obvious as well. But you have to explain what they are, what they mean in terms of application. I've said that, I don't know, probably 100 times this year. Because they are significant. And even students, even when they get to master's level occasion, they get the difference between being wrong. All right, you need to know what they are. What is Young's modulus? What is Young's modulus? Yeah, no, don't give me technical then. What does it mean in practice? Well done. How difficult is to deform it? Not shape it. How difficult is, for example, to bend it? Is stiffness, rigidity. How do you measure it? Okay, can you make a note of this? Make sure you understand it and know how to measure it. You measured it. The reason is, okay, I put this question, why? Because you're actually in the lab, you looked at it, didn't you? Or have you forgotten all about that?
No, we have. It's yes. Yes. No, we haven't.
Remember it.
We haven't.
Okay.
I was still to get him like.
Yes, please. You've got at least one exam paper, previous exam paper.
Yeah.
You also have notes. Please read them and come here next week with questions. Say you don't understand that, what does it mean? Or what does it mean in terms of application? Okay?
Yes.
Do you want to give me your laptop and I'll stay on charge for a minute?
No, because I'm not going to use the bus.
Yeah, I know, but when you get home, I just can't get it.
I'll just plug it in, won't I?
Okay.
It's alright, thank you then.
Yeah, but I am in no rush right now.
That's fine. In fact, I got